All right, so now let's evaluate explicitly what is the statistical entropy when you have this Bose-Einstein occupation, which we had written before as an I plus the degeneracy of the level in question minus 1 factorial divided by an I factorial and epsilon I minus 1 factorial. Okay, so that's the thing. Let me, yes, e factorial minus 1, that's the thing. Okay, so we again do the same thing. I'm going to do it like step by step because in the lecture notes I kind of skip something, but you know, this is just because we have done it so many times. We want to calculate the Boltzmann entropy, and this is just proportional to the logarithm of this thing, and the logarithm of this thing in this case is just the sum over the energies. Here you have the logarithm of an I plus the degeneracy of the level in question minus 1 factorial minus, the whole thing is in the sum, right? So minus the logarithm of an I factorial minus again the logarithm of this gi minus 1 factorial. Okay. So we can again apply Stirling's approximation. These guys are always going to be large, and actually we can already like make a second approximation, which is if these guys are large. Anyway, these guys can be thrown away like easily, right? So this is what we do. We say that SPK is approximately equal to the sum of, if you like to write it like this, EI minus 1 logarithm of what is parenthesis logarithm of ni plus gi minus 1 and then minus 1 again, so it's a quite cumbersome expression. Here you go, minus 1 minus ni logarithm of ni. Now here we could say that this thing is very large and apply again this Stirling's formula, but we're not going to do it because we don't know first, and we also don't need to do it. So let's just write it as is, logarithm of g like that minus 1 factorial, whatever that is. Okay, so this is what we have. Like I told you before, no, because this minus 1 is just tiny compared with this thing, you can throw it away and that's fine. Okay, so we can just do that straight away. And remember, what we want to do is to use the method of Lagrange undetermined multipliers to find the values of n that maximize the statistical entropy in a system which is thermally and mechanically insulated, constant energy, and Clausius inequality becomes the principle of maximum entropy there, and we want to maximize entropy. That's what we are doing. Okay. So the constraints once again are that there is some fixed number of particles, so somehow the sum over the energies of the different occupations minus the total energy is something that has to remain 0, and then this also, the total energy has to remain constant even if I wiggle around these ends. So these are the constraints of my optimization problem. And the whole thing, the variation of this whole object with the corresponding constraints and the multipliers has to be equal to 0. Okay, so now let's just do the differentiation of the variation here, and what you get from the first term is the sum. Let's just do the sum over EI of the variation of NI, and what you get inside of here is from the first term just the logarithm of NI plus GEI. I'm throwing away the minus 1 like I told you before. You can keep it like in the lecture notes and throw it away in the end, but it doesn't make any difference. Second thing would be just 1 plus 1 here. Then from this term you get, as usual, minus the logarithm of an I minus 1, From this term you get nothing because it really doesn't depend on n, it just depends on the fixed degeneracies. And then from the constraints you get the usual contribution, so the minus alpha and the minus beta times ei. Okay, so the whole thing has to be equal to 0. For arbitrary variations means the bracket is going to be equal to 0. And what this is saying is that, well, if you like to write it like this, log of n divided by ni plus g of ei. This goes with that. And on the right hand side you have minus alpha minus beta epsilon I. So, okay, you exponentiate and whatnot, so let's just do it. Here you have, well, probably it's better to do it the other way around. This is just more straightforward. Let's just do it like this. We multiply everything by minus 1. Just do it like this. So this is alpha here plus beta ei. Exponentiate so that we have ni plus gi equals to e to the alpha e to the beta ei. Now, you know, this is 1 plus this divided by n. Just write it like this. Ni plus 1. The 1 can go to the other side. We put the 1 in the other side. We flip this thing, right? Because we want ni. So ni divided by g ei is 1 over this thing. 1 over e alpha e to the beta ei minus 1. And then this g, I can get rid of it, throw it to the right hand side, and I end up having what I wanted to have. Okay, so this thing is the equilibrium occupations according to, well, for identical indistinguishable particles, and it's what's called the Bose-Einstein occupations, okay, or distribution. Okay, so you see the only difference with the Maxwell-Boltzmann is that there is this additional minus 1. This insignificant tiny minus 1 changes a great deal of things, okay, but this is the difference. So now we are going to see what happens with fermions, okay, and what happens with fermions is very similar except for the fact that you cannot bunch different fermions together in the same state. You can't do that because of the exclusion principle, and this changes again the formula that we get. So we are going to see that in a moment in the next video.